All right, 14.4. It's titled on here, Permutations and Combinations. More generally, it's titled what your notes say, which is Counting Techniques and Probability. And we're going to encounter ways of counting things. So our leading idea is the following. Permutations and combinations help us understand the different ways elements can be arranged or selected, highlighting the vast possibility within a structured system. Similarly, faith in God acknowledges the many paths and choices life presents, while trusting God rather than random chance. Just as mathematics explores how different outcomes can arise from various arrangements, faith in God embraces life's complexities with confidence that there is meaning and order beyond what we can see. Let's pray. Dear Heavenly Father, I thank you for an opportunity today to start our last section of material. I pray that the details that we work with and the counting strategies that we learn would be reasonable, would make sense, that good questions would be asked, and that you would help me to provide clear answers. We pray these things in Jesus' name. Amen. Have you seen factorials before? Exclamation point. Okay. N factorial means that you take the number n and you multiply it by one less than that, and then one less than that, and then one less than that, all the way down to 1. Okay? We stop at 1, so if the n were small enough, I probably wrote down more things than I needed. But in general, we're multiplying a bunch of numbers together sequentially as we go downwards. And 0 factorial, by definition, is the number 1. It doesn't fit within the description above. It needs its own definition. 0 factorial is the number 1. Okay, so far so good? And we're going to do a real quick example of that, and then we're going to see how it's going to be used in a little bit. 4 factorial. What would that look like using that first definition? Mackenzie, you can help me out. Which is 3, and then 4 minus 2, 2, and then 1. Yeah. So we start with 4, and we multiply by each integer, or each whole number in this case actually, that's going down until we get to 1, and we multiply it out. So what is 4 times 3 times 2 times 1? 24. So 4 factorial is the number 24. There is a fundamental principle of counting that shows up in chapter 2, and we revisit it here in chapter 14. It says the following: if m, an event m, can occur in little m ways, there's a typo there, sorry about that, and event capital N can occur in little n ways, then event m followed by event n can occur in mn ways. Okay, so this has to do with making choices or outcomes of some kind of an experiment. So let's say you had an experiment getting dressed this morning and you had to make a clothing choice. You all did. And we'll just make it simple. We'll just talk about your shirt and your pants. Okay, if you counted all the shirts in your closet and you counted all the pants in your closet and you multiplied those two numbers together, that's how many outfits, aside from whether they match or not, you could wear today. Make sense? That's the idea. Okay, so that's the fundamental principle of counting. We're going to do an example. Pizza Planet. Pizza Planet offers 3 kinds of salad, 15 kinds of pizza, and 4 desserts. How many different meals consist of 1 salad, 1 pizza, and 1 dessert? So whenever I do fundamental principle of counting, I write space holders for the number of events that they're describing, in this case 3. I need to choose a salad, I need to choose a pizza, and I need to choose a dessert. And within those number spaces, I'm going to write the number of choices I have. So how many choices do I have for salad? 3. For pizza? 15. And for dessert? 4. And the fundamental principle of counting says I'm going to multiply those together to find how many different meal deals there are at Pizza Planet. So when you multiply this for us and tell us what you get. There's 180 meals. So I don't know if you guys are old enough to remember, but Sonic did this at one point where they talked about the number of drink combinations this is essentially what they did. They multiplied the number of different outcomes you could choose by adding flavors in their drinks with the number of drink options they have to begin with. And I'm sure it's more than it was before because they've added flavors, okay? But this is what they would have done. This is the type of calculation for that. So one method of counting is fundamental principle of counting. Second counting method is called permutations. And specifically, this is permutations of like objects. So I'll describe what that means in a second. But the way that this works is if you have n elements, and some of those elements are like other ones. So R1 of them are alike, indistinguishable, can't tell them apart. R2 of them are alike, indistinguishable, can't tell them apart. Then the way that you can figure out how many ways in which are distinguishable outcomes is by taking n factorial and then dividing it by each of those things that are indistinguishable. I'm not able to tell them apart. So examples of this, we got one showing up, but one example of this would happen if you were looking at cars. So we'll do a car example. So if you were outside and you were counting cars and you were counting only the make of the car, right? Who made it? Chevy, Ford, Toyota, whatever, okay? And if that's all you were looking for. So that would mean that any Ford is indistinguishable from any other Ford. Okay, so if we went out the parking lot and we counted all this, right? Any Ford indistinguishable from any other Ford. Then we would take the total number of cars in the parking lot on top, and then we'd write the number of Fords that are indistinguishable. We'd write the number of Chevys. We'd write the number of, whatever they are, they would all be in the denominator. Okay? So whatever characteristic or whatever trait that's being talked about being indistinguishable is what we're talking about. It doesn't necessarily mean that we're talking about something that really is indistinguishable, right? I can tell that that's your car. It's got a sticker on it and the other car doesn't, even if it's the same make, model, and color, right? Whatever. So that's not what we're talking about. We're talking about looking at a specific characteristic of something. Now, the next one, you don't even need to look at characteristics. You just get a package of Starburst. Okay? So in a package of Starburst, there are 4 red, 5 pink, 3 yellow, and 2 orange. Okay? Every pink Starburst is indistinguishable from every other pink Starburst. True? Yeah. Okay? So candy is a really good example of this. You can do this with just about any kind of candy that has colors. So think M&Ms, think Skittles, right? All these things would have this kind of a feature to them. And if you're asking yourself how many ways you could eat them, right? You're saying if I eat a red and a red, it doesn't matter. But if I eat a red and then a purple and a red, that's different, right? These things are counting in different ways. So how many total Skittles are represented here? Just counting Skittles right now. I didn't mean Skittles, Starburst, sorry, Starburst. How many? 14. I have 4 red, I have 5 pink, I have 3 yellow, and I have 2 orange. There's 14 total. Okay, everybody with me so far? 14 total Starburst in my package. I don't know if that's right or not, but somebody can tell me later. That sounds like too many actually, but that number is gonna go on top. And then on bottom, we're going to put the factorial pieces for each one of the indistinguishable colors. For example, I have 4 red, so that's 4 factorial. I have 5 pink, so that's 5 factorial. 3 yellow is 3 factorial, and 2 orange is 2 factorial. Okay, all good so far? I would like for you to resist the temptation to look at this and say, hey, 14 divides by 2, and I'm going to do that. 14 does divide by 2, but those factorials on the end don't let you do that. So what I'd like to do is to write them all out and to show you first what it looks like all written out, and then I'll show you an abbreviation that you can use so that you don't have to write them all out. Okay, so there's my numerator all the way down to 1. And then I've got my denominator, 4, 3, 2, 1. And then 5, 4, 3, 2, 1. And then 3, 2, 1. And 2, 1. Lots of things. Now it's written in this form, so we actually can cancel components of things out. What I'd like to notice with you is that the biggest factorial in the bottom, 5 factorial right here, is also right here. Do you see that? So we could sort of cancel a whole block of them out at once if you'd like, and that's what I'm going to recommend. And if we think about it from that perspective, what we could have done instead is when I noticed that I get to the smallest or the largest factorial that's in the denominator, 5 factorial on this list, I could stop and that 5 factorial could be written with only the other pieces written out. All right, you with me? So I can stop short as long as they match completely, I'm able to cancel them. 5 factorial, 5 factorial. I can't divide them, but I can cancel them completely. So depending on which one you look at, it doesn't really matter. We're going to go through and we're going to cancel terms. Everything in the denominator will cancel out. You will not end up with a fraction or a decimal. Because remember, what we're doing here is we're counting the number of ways something can happen, and the number of ways something can happen cannot be a decimal or a fraction. That wouldn't make sense, right? This isn't a probability. This right here is just a counting value, right? Whole number. So we're going to go through and we're going to find some things that work out nicely. For example, 4 times 3, that's nice. That's 12. Okay, what else do you see that might be nice? 3 times 2 is 6. And if you cancel them in a different way, it's still going to give you the same answer. It doesn't matter. I don't have 2's individually on top, but I do have values that divide by 2, right? So I could divide the 2 into the 14 and to give me 7. I could divide this 2 into either the 10 or the 8. I'll go with the 8 and give me a 4. So I wouldn't say trickiest, but the place where you need to be the most careful is right here, that you don't lose any of the values that are not canceled. So I'm going to go back and I'm going to select them. Hopefully I'll get them all. I have a 7 and I have a 13. I have an 11 and 10, a 9, a 4, and a 7. And you're going to multiply them out with your calculator. And you're going to get a very large number. So somebody grab a calculator and multiply 7 times 13 times 11 times 10 times 9 times 4 times 7. What do you have?
2,522,520.
That's what I have. There are over 2 million ways that you can eat that package of Skittles, or Starburst. It's still Starburst, sorry. Maybe I should make it Skittles next time. Okay, so whenever we're working with this particular strategy, it's involving things that are alike, all right? So if you looked at some sort of package of candy and none of the pieces of candy are alike, it doesn't fit with this strategy, okay? I mean, we can't give the bag of, Rolos. They're all alike. It doesn't make sense. Okay, so third strategy. These are permutations of unlike objects. So these are places and cases where every single object is distinguishable based on some characteristic. Okay, you can tell them apart. So when that happens, it's important for you to realize that in this case, the order matters. The order matters in permutations. It mattered in the last one too, that was the whole point. But the order is going to matter here, and I'm mentioning it because we're about to encounter one where it doesn't, okay? The order matters. Now this notation here is permutation notation, and it says that we're going to take n objects, and we're going to choose r of them. Okay? So in this room, if we were to take everybody in this room, we count everybody up, we would be the n total. And if you wanted to choose 3 people, and those 3 people got money or something like that, right? In different amounts. This is what this would be counting. Okay? You're choosing among 3, or choosing 3 from among however many. So on the top, you have n factorial, so total number of choices. And on the bottom, what you actually have is the total number that weren't chosen. If I choose r, then n minus r is the ones that weren't chosen. So the reason that shows up in the denominator is because those n minus r that are not chosen are now indistinguishable because they were never chosen. They become like the red starburst. I can't tell them apart because I didn't pick them to begin with. Okay? So that's what you're dividing by. So let's take a look at an example. This is similar to what I was just describing. 30 contestants put their names in a hat for a raffle. First place wins $100, second place wins $50, and third place wins $25. And how many different ways can the prizes be awarded? So what this is telling us is that we have 30 people that we're choosing from, and we're picking 3 of them to get prizes. We don't have quite 30 people in our class, but other than that, it's pretty similar. And the order matters because they each get different amounts of prizes. Okay, I'm harping on that because I'm about to do one that doesn't have that feature. Okay, it matters whether you're chosen first, second, or third out of the hat. So we have 30 factorial. That's the total number of ways of choosing from among 30. And on the bottom, we have the number we don't choose. So if 30 people are in the room, or in the hat, and 3 are chosen, how many are not chosen? 27. So feel free to write down 30 minus 3 if you wish, but the denominator is really the people in this case that are not chosen. So 27 of them. Now, I don't want to write down 30 factorial all the way to 1, and neither do you. So in this problem is a very good example of a case where I want to use that strategy that allows me to stop short. So 30, 29, 28, and then we stop at 27 factorial because 27 factorial matches the denominator exactly. I'm able to cancel those out because they match exactly, and then I'm able to multiply the remaining pieces. So I have 30 times 29 times 28. Let me know when somebody has that. It's more than that. Oh, you said 24. I heard you say something different. Sorry. You said 24, right? Yes. Yeah, you're right. Sorry about that. 24,360 ways. It's a lot of ways of choosing 3 names out of a hat. True? It's a lot. Now, I'd kind of like you to notice that this actually also has the ability to be done with the fundamental principle of counting if you wanted it to. You have 3 choices to make. Choice number 1 is 30 people in the hat, but once you pull out that person's number, name whatever, there's only 29 left, and after that there's only 28. You could do this with the fundamental principle of counting, and it would also work. Combinations now. A combination, the order doesn't matter. So in this case, we still have n elements, and we're still choosing R. But you're choosing them almost like you're choosing a group to do something. You're not choosing them as individuals. So the order in which you choose those group of people doesn't matter either. So you see the denominator. These are the people that aren't chosen, n minus R. Okay, they're indistinguishable. But the R people are also indistinguishable because it didn't matter how you chose them either. They were simply chosen versus not chosen. Okay, so what this looks like in a problem is like the next one. We still have our 30 contestants. They still put their name in a hat. 3 of them are still going to win something, but they all win the exact same prize. So now it doesn't matter if they're chosen first or second or third. It's the same prize given, right? It's indistinguishable how they were chosen. So we have 30. It's a combination, and we're choosing 3. 30 factorial. 27 are not chosen. 3 are. Okay, the 3 people that are chosen are indistinguishable. The 27 people that are not chosen are indistinguishable based on this characteristic. Does that make sense? Now I do have 2 numbers with factorials in the denominator. I want to stop at the first one that I match. So I'm still going to stop, in this case, at 27. So 27 factorial is my stopping space still. And then I have the 3, 2, 1. So 27 factorials cancel. The 3 and the 2 will cancel with something on top. So somebody tell me what you want to cancel them with. You have choices, but 3 and 30, sure. That gives me 10, right? And then what? 2 and 28, or you could do the 2 and 10. So 2 and 28 would give me 19. That's not right. 14. That's not right. What am I doing? 14. Thank you. Wow. Okay. I was thinking about 38. All right. So my numbers are 10, 29, and 14 that I'm multiplying this time. Clearly, it's going to be smaller than the last one. That should make sense from the formula already. I'm dividing by something extra. So if the order in which I chose the people's names didn't matter, how many ways could I choose them? 4,060 ways. Far fewer, right? Far fewer. All right, the rest of our examples are all taking a look at the same things, but they're all sort of intermixed together because that's more kind of realistic of how you're going to see these problems. You have to decide which of these strategies will work, and sometimes there's more than one, and which one should I try, and so forth as I'm looking at them. So here's our first one. If all phone numbers in a large business are 405-767, and then there's 4 numbers after it, how many different phone numbers are possible? Okay, what do you think? We have 4 options. We have fundamental principle of counting. We have permutation of like objects. We have permutation of unlike objects. And we have combinations. What one most closely resembles this problem? All right, here's a tip. When you have the ability to repeat something, right? I can repeat the numbers, right? I could put the number 1 in all 4 of those last spaces. When I have the ability to repeat something, it's going to be a fundamental principle of counting. And the reason is because none of the other options did that. Think about our raffle. Once I pulled their name out of the hat, they didn't put the name back in the hat and get chosen a second time. Okay? So once I've got the idea that I can repeat values, I'm going to have to use a fundamental principle of counting. So how many values can I put in the first of those 4 missing digits? How many numbers do I have? There are 10. It's 0 through 9, right? How many can I put in the second position? 10. And in the third? 10. And in the fourth? 10. And the fundamental principle of counting will then multiply those together. What is 10 times 10 times 10 times 10? I think it's 10,000. Is it 10,000? 1 with 4 zeros because there's 4 zeros present. 10,000. So there are 10,000 numbers that this business would have available if they have all of those features at the beginning and only the last 4 different. Okay, let's take a look at another one. A worship team practices 8 songs on Wednesday night for a Sunday service. If the worship minister plans to choose only 5 of the 8 songs practiced, in how many ways could the songs occur? What do you think this one might be? It's very close to a combination. There's a phrase, huh? What were you saying, Hannah? Yeah, they're unlike objects. This phrase right here that says, in how many ways, is one of our red flag phrases. Now you'll know. When you're looking at how many ways something can happen, you're looking at a permutation. Because you're not just choosing a specific group of, 5 songs. You're looking at the order in which you play the 5 songs. Yes, ma'am.
So on example 5, when we did the combination, it says in how many different ways. So how would you be able to...
Because of the context. The context had the prizes being awarded, and we knew the prizes were the same. That's how we would know. That's a very good point. Because the prizes are the same. Was why that wouldn't have happened that way. Okay. We could also look at context on this one. So y'all been in a worship service before. Does the order in which the songs that somebody plays matter? Yeah, it does. There is usually a crescendo to a point, and then there's a decrease. People choose songs in specific orders very specifically. It's on purpose. The order in which the songs are played matters. It makes it different. So this one is a permutation. It is unlike objects. So we have 8 songs that we're choosing. And we're going to choose 5 of them.
Wait, how is it unlike objects if they're all songs?
Because the songs are different.
Oh.
Yep, the songs are different. All right, so 8 factorial goes on top. And I'm choosing 5 of them, so how many am I not choosing? 3. So 3 factorial goes on bottom. I have 8, 7, 6, 5, 4, 3 factorial where I get a stop. to match. The 3 factorials cancel. What do you get if you multiply these out? 6,720 ways. This one could have been done with fundamental principle of counting as well. So if anyone was thinking, well, could I do it that way? You could. You're choosing 5 songs. There's 8 choices, and then there's 7, and then there's 6, and then there's 5, and then there's 4. Assuming you're choosing 5 separate songs, right? Not repeating a song in there. And you would have gotten the same thing. All right, we're going to do a magnified problem. It's got lots of parts to it because it lends itself so well for practicing these techniques. We've got a standard deck of cards. So it doesn't really matter what game you're thinking of. Phase 10. Hand and Foot's one that we play. Go Fish. Old Mate. What games have cards? Skip-Bo, Uno, okay? Poker will work too. But any card game has this feature that I'm about to describe. Anyone has this first feature. The order in which somebody gives you the cards, what's the first thing you do? After they've already shuffled. Somebody gives you the cards after the shuffle. What do? You order them. And depending on the game, depends on how you order them, right? So there might be a specific number order you're putting things in. Maybe you're putting things in certain groupings in certain ways. But the very first thing you do is you rearrange the cards. Are you with me? Think about whatever card game you want. That's the first thing people do. Because rearranging the cards doesn't change the cards that are in your hand, the order in which you got the cards didn't matter. Right? Okay. So since the order in which you got the cards didn't matter, which type of problem is the card games? It is a combination, because combination is the only one in which the order doesn't matter. Okay? So these are combination problems, all of them. Now I'm going to read out, or not read out, but say out some details about decks of cards. If you're unfamiliar and you need to write them down, do so. If you're familiar and you don't want to write anything down, then don't. In a standard 52 card deck, half the cards are red, half are black. Okay? So how many are red? 26 and 26 black. There are 4 suits of cards: hearts, diamonds, spades, and clubs. So there's 13 of each of them. So there's 13 hearts, 13 diamonds, 13 spades, 13 clubs. Each suit has values of their cards. The values there's numbered cards that go from 2 to 10. So there's 9 number cards in each suit. Then you have 3 face cards: Jack, Queen, and King. And then you have the ace, which is neither a face card nor a number card. Okay? And depending on your game, will play on whether or not the value of the cards does certain things. You play phase 10. Certain cards are 5 points and certain cards are 10 points, right? If you're playing poker, a 9 is better than a 4, just because it's a bigger value, those kinds of things. So our first question is to simply decide how many different 5-card hands can be dealt. So how many cards are there? 52. And we established we're doing a combination. And how many cards are we choosing? 5. So I have 52 factorial on top. And then on bottom, I have not only the number of cards I don't choose, which would be 47, but I also have the number of cards I do choose, which would be 5, because the order in which I received the cards did not matter. So I have 52, 51, 50, 49, 48, and 47, where I'll stop because it matches the 47 on bottom. And then I have 5, 4, 3, 2, and 1. So the 47s cancel. And then again, everything on bottom is going to cancel with something on top. Tell me what you see that cancels.
5 and 15.
5 and 50 give you 10. What's next?
4 and 48.
4 and 48 give me 12. What else?
3 can go
3 can go
into 12.
into 12, and it gives me a 4. Where do you want to cancel the 2 out? 10. 2 and 10 give me 5. So the values I have left are 52, 51, 5, and 4. 5, 49, and 4. Yes. How many hands of cards do I have? It's a lot. That's why you can play card games over and over and over again and they're never the same game again, because it's a lot.
Would be 2,598,960.
Yep, it would be. Approximately 2.5 million different hands of cards. And it would be more if the order mattered, right? But the order doesn't matter. All right, so now we're going to put some restrictions on the cards. The first restriction on problem B that we're going to do is that we're going to look at having a hand that's all diamonds. Okay, so it doesn't have all the other stuff, it just has all diamonds. So if I have a hand that's all diamonds, how many diamonds are there to choose from? 13. Still doesn't matter the order in which they're dealt, so it's still a combination. And how many am I choosing? 5. So 13 factorial on top. I don't choose 8 of them. I do choose 5 of them. So those are my values on bottom. We'll write 13 down to 8. And then we'll write our 5, 4, 3, 2, and 1. This one actually has a feature that the numbers on bottom pair up nicely to cancel with stuff on top. Can somebody find me a pair on bottom that cancels nicely with something on top? 4 and 3 make 12. And 5 and 2 make 10. Just happens that way, right? So we have 13 times 11 times 9. Okay, so now let's be real. 1,000 hands of cards is a lot of hands of cards. It is. But it's not compared to 2,500,000, right? This is uncommon. It is very uncommon to get a hand dealt to you that happens to be all diamonds. So, what then is the probability that we actually get a hand with all diamonds? Because there's a lot of choices, but it's not infinitely many. The other one was much more. Well, we want the probability of getting diamonds. Let me write that differently. The number of ways of getting diamonds over the number of ways of getting anything.
Would that just be 1,287 over 2 million?
Yep. 1,287 over the 2,598,960. And this is back to probabilities, right? We're not looking at odds where we were looking at ratios. This is a probability. So we're going to go ahead and do the division and figure out what the corresponding decimal will be for this. I think we need at least 4 digits. So let's go with 4 digits on our decimal place.
Should be 0.0005 is what it is there.
Yep. 0.0005. Okay, if you multiplied that by 100, that would give you the percent. That would be way less than 1%, right? A 0.05%. Very rare. All right, let's do one more problem. We'll do it really quickly. A committee of 3 people is selected at random from 7 seniors, 5 juniors, 3 sophomores. What is the probability the committee consists of all seniors? So I'm just going to tell us how we work through it because I want to make sure we get it finished. I'm selecting 3 people from among 7, 5, and 3. So 7, 5, and 3 means that I have, how many people do I have? 15. It's a committee. A committee, the order doesn't matter in which they're chosen. So from among 15 people, I need to select 3. This is 15 factorial over the 12 I don't choose and the 3 that I do. My 15 factorial, or my 12 factorials, cancel out. 3 cancels with 15 to give me 5. 2 cancels with 14 to give me 7. If I multiply these together, I believe I get 455. There's 455 different committees that can be formed when we're considering classification, right? Freshman, sophomore, junior, senior. But we want to know how many committees consist of all seniors. So how many seniors do we have? 7. So we're going to choose just a senior committee. There's 7 factorial. I don't choose 4 and I do choose 3. So this is 7, 6, 5, 4 factorial on bottom, cancels with the 4 factorial. And then my 3, 2, 1. 3 and 2 very nicely cancel with the 6. 7 times 5 is 35. So there's 35 committees that are all seniors, possibilities, 455 possibilities of getting any committee. So we would have the number of ways of getting seniors on top divided by the number that's total on bottom. 35 over 455, just like our last problem with the diamonds over the total hands of cards. This reduces as a fraction to 1 out of 13, or if you want to use decimals, and your book likes to use 4 decimals for these, it's 0.0769. So it's about a 7.5-ish chance. The other problem, part B, does the same thing, but it wants to have a committee that has no seniors. So if you have no seniors, it means it's all juniors and sophomores, right? So how many juniors and sophomores do I have? There's 8. So I'm going to choose from among those 8. So I don't choose 5, I do choose 3. My 5 factorials cancel, 3 and 2 make 6 again. 8 and 7 is 56. There's slightly more options of this happening. Not a lot, but slightly more. And again, the number of no seniors is on top. The number of all of them is on bottom. So 56 over 455 reduces to 8 over 65, which is approximately 0.1231. It doesn't matter to me if you use decimals or fractions there at the end. I'm just giving you choices.